Okay, now we're going to learn Flemming's left-hand rule. This rule applies whenever we have a current-carrying conductor that is inside a magnetic field. We use this to determine the direction that that current-carrying conductor will be forced. So what Flemming discovered, that if you take your left hand and you use your thumb, your first finger, and your second finger, and you put them mutually perpendicular to one another, or in other words, if you have your thumb pointed in the upwards fashion, your first finger would be 90 degrees to that thumb, and your second finger would be 90 degrees to both your first finger and your thumb. So you would hold your hand in this position. Now, up here I have a magnet shown with the North Pole on my left and the South Pole on the right, and my magnetic field lines are flowing from left to right. And in the middle of that, I have a current-carrying conductor. Currently, it has no current in it. We're going to try current in both directions and see how it applies in this rule. So the first test we'll do is I'm going to put a plus sign here, and a plus sign will indicate that conventional current is flowing out of that conductor. So you could think of it as the positive terminal on a battery. The current is flowing out of that terminal. So I will point my second finger in the direction of that current flow, so it'll be pointing out of the board, just like our current is. The first finger will be pointed in the direction of our field lines, or from left to right, and our thumb is going to show us the motion in which that conductor is going to be forced or up. So in this particular application, my conductor will be forced in the upward fashion. Let's do another case here. I am going to reverse the current flow in the conductor, which I will denote with a negative sign. And that means that current is flowing into the whiteboard. You can think of it much like the negative terminal on a battery, where in a circuit the current is returning to the negative terminal of the battery. So in this case, we'll take our Flemming left-hand rule, but for me to point my second finger in the direction of conventional current, I'm going to have to turn my hand over, and it's going to be pointed into the whiteboard. My index finger is still going to be pointed in the direction of my magnetic field lines, which is going to be left to right, and my thumb is going to indicate in this case that this conductor is going to be pushed in the downward fashion, so in that direction. Now, to remember the fingers and what they represent, if you just write thumb and you write down first and you write down second, the M in thumb is the ultimate motion that we're trying to determine. Okay? The first finger is going to be my field, or field lines. And my second finger, if you underline the C, would be for current. Okay? So we use the current and the magnetic field lines to determine the motion. And that is an application of Flemming's left-hand rule, or the motor effect. Okay, here we are at the bench, and we are going to do a demonstration of Flemming's left-hand rule, or the motor effect. And what I have set up here is a magnetic field with my north being here, my south being there. And I have a coil of wire that is inside the magnetic field, and I have a battery here that I am going to use to induce a current in that conductor, and we're going to see the movement. So here, this lead has the positive terminal on it, so this would be similar to our first demonstration that we did at the board, where I have current coming out of this conductor towards the camera. So I am going to touch my lead to that battery, and we should see this conductor go upward. And indeed it did go upward. I am going to reverse the leads to reverse the current in there, and we should see that coil of wire go in the downward fashion. So that proves the theory that we did at the board of Flemming's left-hand rule or the motor effect.